This is the Tenaris team, and my name is Jay. This is Doug, and we also have team members Lucas and John. So we were presented with a problem from Tenaris, a leading coiled tubing manufacturer, with the problem of what we would do when the industrial cost is increasing, as well as the raw materials, but when the price is decreasing. So in order to tackle this problem, we are to look into reducing the industrial cost and increase productivity. So the scope of our process is going to be with 3 departments. First, it will be the 4 assembly lines. Then it will be the 2 milling, depending on the diameter of the pipe. And then it goes to some percentage of the product will go to the heat treatment department. Our first step in tackling our problem will be finding the bottleneck, in which Doug here will further explain.
Alright, so Tenaris provided us some historical data over the past year of basically their analysis of how their departments and lines within their departments performed. So in order to find the bottleneck, we needed to calculate the effective productivity of each department, which is displayed by this formula. So in the data provided by Tenaris, we were given the productivity capabilities of each server within each department, the utilization that that server witnessed over the past year, its cycle time ratio, its scrap percentage, or the amount of materials it had to throw out over the past year. And by multiplying these all together, we were able to determine the effective productivity. As you can see in the middle table here, that's the sum of all 3 departments. Now, in order to identify which department is our process bottleneck, we need to find which one is the lowest number. So at first glance, it seems like heat treatment is the bottleneck because its number is significantly lower than the assembly and the milling. That's not entirely true, as witnessed at the process flow. Not 100% of materials from milling make it through heat treatment. Weight, the effective productivity, we need to multiply the effective productivity in the assembly and the effective productivity in the milling by the percentage of materials that went through heat treatment. Shown here in the last table are the projections of what percentage of materials that Tenaris thinks will run through the heat treatment. So up until 82% of materials running through heat treatment does milling remain the bottleneck. At that critical point, the bottleneck will flip into the heat treatment. Now, this is assuming that all the numbers provided by Tenaris remain constant over the next few years. Alright, so the next step in our analysis, we created a simulation model in a software called Simio in order to verify and validate the numbers provided by Tenaris. And now the simulation model is representative of the process. So as you can see, this table verifies our model, but there is one discrepancy that I'd like to address. Given the low quantity of materials that currently run through heat treatment, Simio interpreted that as a very low utilization for the heat treatment server, which produced a very large error in the effective productivity for what Tenaris projects heat treatment to be compared to what our model suggests. Now, this is due to heat treatment being a brand new department that Tenaris has only recently finished. Numbers that they gave us for heat treatment were based off projections from other heat treatment departments in other facilities that Tenaris owns. Now, the problem with this is all those heat treatment departments over in their other facilities, those are for seamless straight pipe and not continuous coiled tubing.
We've altered the parameters to better fit the model. In our calculations, we found that the bottleneck would not shift to the heat treatment until the mix would be 82% or in their projected at 2020. In result, we decided to leave the heat treatment outputs analysis. Now we will look into our recommendation. We know that the bottleneck is at our milling department, so our recommendations are considering in ways to improve productivity in milling. The chart here will show the comparisons of our recommendations. Our first bar represents the base model, or what represents the current process, or productivity in the process. We have the assembly here and the milling here, and our first small recommendations we looked into was implementing or investing in more big wheels, which is what holds the steel flat that is produced by the assembly and then transferred to the milling. As you can see, there's a small increase in productivity. In our next bar, we see the implementation of a second abbey, or the third milling line. This increases the productivity immensely. It is roughly actually 16% increase in productivity. Or the recommendation, we look at the implementation of adding more big wheels as well as after, Now we will look at the last bar graph, in which we implement the investing of big wheels after we have
the second abbey line.
The blue bar you see here is a recommendation of implementing a second abbey or a third milling line. This increases productivity immensely, and for the milling increases about 16% increase in productivity. The fourth bar you see is the recommendation of implementing both the second abbey as well as a total of 11 big wheels.
In order to determine the optimal number of big wheels for the base model and for the model with the second abbey line, we did a sensitivity analysis within Simio by increasing the amount of big wheels one at a time in order to determine the optimal amount. Now, for the base model, the optimal number was 10 big wheels, and for the model with the second abbey line, that was 11 big wheels.
Our next recommendation is to implement or to invest in airlifts, or what we'd like to call hover lifts, for the big wheels. This will not increase or decrease the time to move the big wheels from the assembly to the milling, and thus decreasing setup time, but rather it will free 2 employees from helping to move the big wheels and freeing up their time to help decrease the setup time where they're needed elsewhere. And Doug here will further explain the analysis.
During our field visits to Tenaris, we learned that in the milling setup that moving the big wheels from assembly to milling takes about 15 minutes. Now, since the hover lifts would free up the 2 of the 3 workers that are ordinarily required to move a big wheel, those 2 workers can then spend their 15 minutes that they would have towards reducing mill setup. So here we've identified a range of 15 to 30 minutes of reduced milling setup time, reflecting those 2 workers being able to go assist in the process, and the associated percent increase in annual productivity. The top line is our sensitivity analysis for before a second abbey is implemented, and the line below is for after a second abbey line.
And our next recommendation based on this as well is to hire a string setup crew. Tenaris can also use this sensitivity analysis for when they want to decide to increase their milling employees. The more milling employees they have can help reduce the setup time up until a certain point. Our last recommendation that we will consider is the cross-training assembly employees to help reduce the setup time in the milling. Now, the setup time, or the setup for the milling, happens around every 2.5 to 3.5 hours. So whenever the setup is needed, one of the assembly line will be shut down, and their employees will help reduce the setup time. With our Simio model, we decreased the setup time for the sensitivity analysis.
What we did was whenever an entity went into string setup for milling, we shut down one of the assembly servers, simulating those workers moving over to the milling to assist in the string setup in that department. We did a similar sensitivity analysis and reduced setup time as we did with the previous recommendations. And as in the last recommendation, we highlighted a zone of 15 to 30 minutes of reduced milling setup time to simulate 1 to 2 workers from assembly coming over to assist in the string setup. And on the graph, we also showed the percent increase in annual productivity that those workers would help achieve.
In conclusion, for short term, we recommend cross-training assembly employees to help with the setup and milling. This will help in the increase of 15% productivity annual. Long term, we recommend the implementation of a second Abbey along with the total of 11 big wheels and the airlifts.